Good morning. I'd like to get this session underway, if possible. As you know by now, things run on a very tight clock, and that clock is here. So things are going to move right along. If you're a speaker, you should be either sitting to my right or to my left. If you're an odd-numbered speaker, you should be here. An even-numbered speaker should be there. You'll have your 3 minutes. When the 3 minutes is up, you'll be done. Don't be mid-sentence when that happens, because your microphone really will go dead and the computer screen really will move to the other person. So don't be the one that's in the awkward position. I'd like us not to have applause individually after the 3-minute talks. I'd be happy for us to have applause after the keynote talk. No time for questions today after any of the talks, including the keynote talk. Having said all of that, I'm very happy to present to you the keynote speaker for this session. I'm now slowing it down while people percolate in and find their seats. The speaker for the keynote session is Steve Laval. You can see that the title of his talk is From Robotics to VR and Back. I'm a professor at the University of Illinois, which is part of the reference of back. We're delighted to have him back at the University of Illinois. I'm delighted that he's still hanging out with roboticists, and I give it to Steve to give you his talk.
Thank you very much. Very happy for the honor to be here and give this presentation. As Seth said, I'm both at the University of Illinois. I've returned back to Champaign-Urbana, but also continue to work for Oculus and Facebook. So I want to give 3 main messages during this talk, and one of them is that virtual reality is big, really this time. So if you've been around long enough, you've heard that before. I'll try to convince you why it may be different this time. My background in robotics was useful for virtual reality, and I want to convince you that yours quite probably is as well. And 3, there are exciting research challenges that lie ahead. And I want to try to convince you of that, and you may find this an interesting area of research to get involved in some way. So my talk doesn't go in this order, but these are the main themes. So to kind of tell you a little bit about myself, so after working on my planning algorithms book back in 2004, which came out around 2006 or so, most of the last decade I was working on foundations of sensing and filtering. I'm very interested in where the information comes from in the robot, in the sort of default planning problem. It's very often assumed that you have everything. And so I got really interested in that, developed things like combinatorial filters with a lot of my colleagues, tried to get down to, for a particular task, what is the minimum amount of information required to solve that task. I made a kind of a short book in 2012, and then went out to Finland on sabbatical in the 2 academic years ago, 2012 to 2013, to write a larger book on sensing and filtering, but then that got disrupted in September of 2012 by a 19-year-old named Palmer Luckey, who started this company, Oculus, in Long Beach, California. And this disruptive technology disrupted my life, and I got involved with the company very quickly and ramped up. As I said already, VR's been around for a long time. I was initially skeptical. It's one of the most overhyped technologies ever. When I was a graduate student at the University of Illinois in the early 90s, I remember they built the cave systems. It was done originally at University of Illinois, Chicago, and then a large group took over and continued to make progress in this front in the University of Illinois Urbana-Champaign campus. A lot of the hype ended in the video game industry with Nintendo Virtual Boy, which was an economic disaster. And so people knew not to touch it in industry, and they were kind of skeptical and scared to touch it. One thing that happened, though, was that the component technology just wasn't ready at that time. And one thing I remember as a roboticist is if you throw us a new piece of technology, it changes what we do substantially, right? I remember when people started playing with SICK lasers all of a sudden in the 90s, it changed the kind of mobile robot research you could do. All of a sudden you have a Wii remote or a Kinect to play with, right? So as soon as you have these great devices that are enabled by other technologies, other markets that are much larger that bring the cost down, you can do amazing things. And so it seemed plausible that virtual reality headsets could be made by leveraging the smartphone industry. So the screens have advanced so much, and the MEM sensors that appear in these smartphones have advanced so much. They're dirt cheap, lightweight, and so you can experiment with them in many different kinds of ways. And so Palmer Luckey and other people that started following the movement, which was mainly from the hacker-maker community, realized that you could build pretty decent systems with a very different kind of methodology just based on current components. So the story went pretty fast. The company was founded around in July of 2012. I started working for the company as a consultant in September of 2012, and it went all the way up to, in March, we announced a Facebook acquisition of $2 billion. And during that time also, we manufactured a development kit, a virtual reality development kit, which involves a headset. We sold about 70,000 or more of those and put them in the hands of developers all over. Many of you may have had a chance to play with that. And there's a new developer kit that started shipping in the past few weeks. And also at about that time, I moved back to the University of Illinois, where I'm building a research lab for Oculus there part-time in the research park, and also resuming my faculty position there. So people have done all kinds of things with this. I just want to flash through like what happens when we throw this device out there, and there's 70,000 of them. There's no limit on age. You can go around and find most of these as YouTube videos if you like. I just wanted to kind of quickly flip through the different kinds of things people are doing with it. So experiences for people with limited mobility, very interesting. Architecture, real estate, so you can put on the headset and feel like you're somewhere else, maybe useful for relaxing or just visualizing new spaces. Virtual reality theater, you can stream whatever movies are on your hard drive, let's say, or live streaming over the internet into a virtual movie theater. You can pick your seats, you can watch it in 2D or 3D. It sounded nearly pointless to me before I tried it, and then when I tried it, it was very compelling. It's actually quite a relaxing experience, and you can try it almost anywhere. It's very nice. Panoramic viewing, so you can look at, somebody connected it to Google Street View very early on in 2013. Now there's all kinds of live video possibilities that are interesting. First-person shooter games, most of the geometry is already there. So Oculus, when it was started, the main target audience was the video game industry, and most of the people are from the video game industry. And so you can very quickly adapt games into virtual reality, fairly quickly, let's say, considering how long it took to develop these games and this whole technology and methodology over many years. When we did a VR game jam, people started making all kinds of different experiences that don't leverage the existing methodology. This is one of my favorites from a VR game jam, where you have a virtual elephant trunk, and you just go flopping it around in virtual reality, moving along a track, just knocking things down. And that ended up being so much more fun than anything else I had played up to that moment. And it's made in a few weeks by people. So I thought that was really great. So the most exciting things are what people just do on their own without any preconceived notions of what the experiences should be like, or without leveraging stuff they've made before. And of course, there's thrill seekers doing virtual amusement park rides. Socializing in virtual spaces. You may remember Second Life. There's also OpenSim, which is an open source platform that a lot of people in universities have been experimenting with. So you can be fully immersed in those environments now and interact with people. They've even had entire conferences. I don't know if I would go as far as maybe IROS in virtual reality, but there are entire conferences that are done in this way now. And then there's just all kinds of interesting art projects and other disturbing things, like, for example, the guillotine simulator. So if you ever wondered what it might feel like, you can look up and see the blade coming down, and then it shows you from your eye's perspective what it might look like as your head's rolling to the ground there. So, and in this YouTube video, his friend whacks him in the neck right when the blade comes down to make it extra terrifying. So all kinds of things out there. Just go search and have fun with it. So we got involved and wanted to perfect the experience, and tried to make things as well as we could. I mainly worked on head tracking technology, tracking the orientation of your head so you present the right images. So there were folks at Oculus in California. We started off working in Finland. My wife, Anna Yershova, and I had a UR5 robot in our apartment. It kind of looks like Scandinavia or Finland there. And we had the sensor on the end effector, and we were doing noise, error characterization, calibration studies, and trying to study the tracking performance. So there's one place where a robot crept in. So the head tracking problem, you have to figure out what to present to each one of your eyes. The eye parts there, inside of the headset, there's just a smartphone screen and a couple of lenses, magnifying lenses. And so each eye is looking at one half of the screen. And so it's also rendered in a distorted way, and then the distorted image that you render gets undistorted because the lenses have their own distortion, and you're supposed to pick the two distortions so that they cancel. Right? So it's very nice. So you end up with hopefully with the identity map when you're done. So that's mainly how it works. The important part for us that looks familiar to me as a roboticist is there's some sensors in there. So there's a sensor board that we had. It's connected to USB and has a microcontroller and InvenSense gyro and accelerometer and a magnetometer. So this provides the data that we need for doing head tracking of orientation only for this part. So you have at 1,000 hertz, you have amazingly accurate gyroscope data, which I thought was really nice. Helped us substantially in comparison to what I would have imagined was out there before. I think these specs are a little bit better than what's in most smartphones, but not too much higher. So it's still pretty low-cost components. It's just leveraging the same manufacturing technology that's already out there. 3-axis accelerometer and 3-axis magnetometer. And so basically we do head tracking, so it's 3 degrees of freedom, as you know, 3-dimensional rotation space. Quaternions end up being pretty useful for this task, and I certainly know that from my motion planning background. People in the game industry use quaternions quite a bit, but it turns out that they're in debates because a few people learn about quaternions and then they say, I know quaternions and you don't, and they start kind of bullying people with quaternions and things. And then the other people who are actually quite clever said, no, we don't need it because our video game character only can pitch their head up and down a certain angle, a certain limit, so they never actually, I'm thinking, oh, they don't reach the kinematic singularity. As soon as I start experimenting with their systems, if they're making a virtual reality system, I look straight up or straight down. That's my instinct as a roboticist. And right away, the world starts spinning around and getting wacky. So it's very interesting. So actually, it's not just, in the debate of whether or not one should use quaternions, it was very interesting that knowing the geometry of SE3, SO3, the space of quaternions, space of translations and rotations, knowing these kinds of things in like our everyday language and everyday comfortable concepts for us as roboticists was very helpful. So you can just take the gyro readings and just integrate them by just constructing a quaternion where the axis of rotation instantaneously is just the normalized gyro output, nothing more, and the angle is just the magnitude multiplied by delta t for a simple Euler integration, and that's all you do. It's amazing how many different places it's wrong or way overcomplicated in various forums and blog posts and other things that people are reading in a lot of places. So very simple. So it's one of the very early things we did in the code. Then, of course, as you know, as roboticists, what's going to happen? You integrate for a while, and there's drift errors, right? So just a standard dead reckoning error problem. This plot was made by one of my former students who joined the company, Max Ketsev. And the drift error rate over time even depends on how fast you're turning your head. Shouldn't be surprising. And if you played around with MEMS gyros or other kinds of sensors like that, you may also have noticed that there's dependency on temperature as well, right? And maybe pressure on the board that the sensor's mounted on, all kinds of crazy things. If you've gone down the experimental end, those kind of things certainly come up here as well and have to be compensated for. How to correct for drift? What do? You need some absolute measurement, right, to compensate for drift. So luckily, there are some vector fields that if we just assume they're constant, just to make it simple, suppose there's some constant vector fields flowing through the space that we're in, then what we do is we divide the 3-dimensional drift error into 2 components. There's tilt error, and we solve that by having a gravity sensor. And then we have yaw error, which is which direction are you facing, and drift in that we account for with the compass. Now, unfortunately, no one gives us a gravity sensor, and no one gives us a compass, right? Instead of a compass, we have a magnetometer, which measures the linear vector sum of the Earth's magnetic field and a bunch of other stuff, including interior fields and fields on the board itself. And we don't have a gravity sensor. What do we have? Accelerometer, right? And that's measuring the vector sum of gravity plus actual linear acceleration. So there's kind of too many degrees of freedom in some way, or too many unknowns. We did a lot of, let's say, hacking and trying various ideas to try to separate these out and do the best we could with it. And I think we ended up with a fairly effective solution. The filtering is quite simple. Just use basic complementary filters over SO3 for the rotational part, and then eventually extended those for translation in a bit, which I'll talk about. There's also some details in our ICRA paper. So I want to start getting into the human perception part. This is a very important part that's certainly there's human-robot interaction, and many of you do research on human-centered aspects of robotics, and I just want to say that it becomes extremely serious in virtual reality, as you can imagine, because we're hijacking the human visual sense and maybe your audio sense as well, and replacing it with alternative stimuli. So at a very, very low level, the human being becomes important. One of the first problems is latency. So when you turn your head, how long does it take for the images to catch up? So that when I turn, what I expect to see is actually there at the right time. That was a killer problem for virtual reality, especially across the 1990s. If you don't get it right, it's either not a comfortable experience, not believable experience, or it makes people sick, right? So those are difficult problems. 2 ways to solve that. One's called image warping or image shifting. That's some technology we use and develop. But another one is predictive tracking, which I worked on. And the idea there is, well, just try to predict ahead to where it's going to be based on a dynamical system model and based on the data that you have. Here I was at an advantage having not worked in virtual reality, because everyone who works in virtual reality was saying to me, yeah, we tried predictive tracking. Sometimes it works, and then when it doesn't work, it overshoots too far, and it's terrible. So I didn't know that. I just naively started implementing stuff for predictive tracking and didn't know that it was a double-edged sword. And so I was thinking about it, and it's like, well, how far into the future do we need to predict, and how far into the past do we need to look at the data from sensors to estimate their trajectory? And it turns out that in the 90s, the shortest kinds of intervals people were considering was 80 milliseconds, and nowadays, or by 2012, it was already down to about 35 milliseconds. So you don't have to predict very far. And so if I look at the upper part there, says, imagine I have a vision system back in the 90s, and maybe it's running at 60 hertz, and it's estimating the orientation of your head. So you might need 100 milliseconds of data to estimate the trend, and then you might have to predict 100 milliseconds into the future. But now, you just need a few milliseconds of gyro data to get a pretty good idea of the trend and filter out the noise, and you only have to predict a little bit further. So the thing I like to say is that you have no free will at 20 milliseconds, right? So due to the momentum of your head, you're going to keep moving the way you were moving. And you need really complicated predictive models, maybe on the horizon of 100 milliseconds or 200 milliseconds. Then your free will starts creeping in a little bit there, right? So it's a control system with unknown inputs is one way to look at it. So I started making different methods, and method 1 was no prediction. Method 2 was add this prediction. Worked fairly well. Then I tried to get really smart and make a better method to estimate angular acceleration, and that was number 3. And did some experiment that looks like this. I put the headset on, and I just turned my head back and forth like this. And I plotted out the data. And so the no prediction at all was the blue line. So the errors in angle, the angular errors got up pretty high, especially when I turned. This is that overshoot that people were talking about in VR. The red method was the new simple one that just extrapolates the angular velocity essentially with a little bit of smoothing. I made this yellow method, and it had way better numbers. Everything's great. So I gave it to one of my colleagues, Peter Giocars. He's an experienced software developer, and he was very keen. He's an audiophile DJ who then turned on the side, kind of, aside from his software engineering career in the video game industry, and he became kind of a videophile. He was very particular about how everything looks in there, and we kept trying to, outdo each other and making things better. And it turned out the better one was actually worse, because when you stare in virtual reality, there's a little more jitter in the new method. So there's a little more noise amplification. It's barely detectable, but it's annoying to people who can see it. But then when you turn, he said, wow, it's great when you turn your head. It really looks great. I can't perceive any error when you're moving. So that prompted us to make a method that does a little of both. So when you're moving, or let's say switches between two modes. So when you're looking and not moving, when you're just staring, let's say, then there's no latency to even talk about. It doesn't matter. You're not trying to get the world to catch up. So it's just doing the natural kind of smoothing that it has. And then when you're exercising a quick motion, then it smoothly ramps up and takes into account the full latency interval and does prediction. So it smoothly blends the two, and that ended up being very nice. So that got me really excited about human perception. I ended up hiring a couple of perceptual psychologists / vision scientists. And we kept pushing further and further, trying to get to the bottom of these things, studying this research-wise, scientifically. And in thinking about it, and this is no surprise to people who've worked in virtual reality for many years, there's a perceptual psychology, vision science aspect all over the place. So all these different problems we're fighting, not just latency, but all kinds of different things we were dealing with. If we don't get it right, we end up with problems of disbelief, fatigue, simulator sickness. It's very hard to study because of adaptation and variance across people, especially adaptation for the people developing the technology themselves. So you might look at it and think it's just fine, and it might be terrible for somebody else. So all kinds of problems like this. Let me give you one example. Take the human vestibular system. So it's another sense that we have not hijacked. It's in your inner ear. It's two parts to it, one on each side. It's symmetric. This is another inertial measurement unit. It's measuring linear and angular acceleration. In fact, the semicircular canals, it really is amazing to me that they're almost perfectly orthogonal, down to within a few degrees, just from evolution. It just blows my mind. So it's almost exactly the kinds of things we have in the gyro. And so now, when you move your character around, let's say you're moving a character around in a video game in virtual reality, what should you do? Well, you show the motions in virtual reality, but that's different from motions of moving your head around, right? So if I rotate my head, I expect that to be synchronized between virtual and physical. When you're moving your character around, you observe optical flow, but your vestibular sense does not detect that. It does not register that. So there's a mismatch, and that leads to discomfort. That's a process known as vection. So it's very well known by psychologists and vision scientists, but it's something that you have to pay a lot of attention to as a game developer. What about head position? So if I start moving back and forth, again, the optical flow isn't right because we only tracked orientation. So another thing we did in the latest development kit is we added a camera, and we also improved the frame rate and pixel switching speed, things like this. But we added a camera. We do full 6-degree of freedom tracking. And one of the things I wanted to emphasize to you is robotics background's really useful here. The main contributors to this generation of software are all roboticists. So there's Dov Katz, who was a student of Oliver Brock, and my wife, Anna Yershova, Max Katsev is one of my former students. So the four of us were the main people doing the software part of that for the head tracking. So there's a lot of opportunities for roboticists to go in this direction. There's a growing ecosystem, so many people are getting into it. There's Sony Morpheus in addition to Oculus. We also have had a partnership with Samsung for some time. That was announced last week. So there's a smartphone drop-in solution that's coming out. Google has Google Cardboard, which is a quick do-it-yourself kit. There's many new technology demands. So you can imagine people because once you're staring at screens with magnifying lenses, the resolution's not high enough, right? So there's a continued tendency to push that. And if you need very fast pixel switching, that turns out to cause flicker fusion problems unless you get the frame rate high enough. So you go up and up from there. We have no shortage of people trying these systems, but the problem is that it's hard for them to be perceptually trained, to look for the right problems. Most people are perceptually blind until they've had a lot of experience with these systems. So for future research, we need better visual engineering. We need better tracking systems. People in robotics can help with that. Sensory stimulation beyond vision. Audio, haptic, olfactory, vestibular, all sorts of interesting possibilities. And then all different levels of being able to use these systems, from interfaces, communication, education, sociology. It's human-centered in many ways. Adding robots is very exciting. Here's some places where roboticists can contribute, and I'm done, I think.
Great. Hi, I'm Georg Tanzmeister, and I'm going to talk to you today about trajectory clustering to extract principal directions for autonomous vehicles. So last year we presented an algorithm to detect the road course with sensor information based on local path planning. So the aim is, as you can see here, to detect where the road is heading and also the road boundaries, and also to detect branches and road junctions. A major component of this method is to cluster all the local paths, so to extract the principal directions. And conventional clustering algorithms, such as hierarchical clustering or k-means, are based on some distance measure between paths, and this leads to bad results here because it requires thresholds tuned to specific scenarios. Similar to path homotopy, where paths are equivalent if there exists a collision-free deformation between them, the objects in the local environment determine when paths are similar here, and the similarity is binary. Path homotopy requires, though, that all paths share the same end states, and since this is local path planning, this is not the case here. The basis of the method is the definition of when two trajectories are similar, and they are if all trajectories in between them, if all states of all trajectories in between them are collision-free. So if there exists a trajectory in between them that leads to a collision, the paths are not in the same class. We developed an algorithm based on this equivalence definition that clusters the paths by creating polygons by sampling intermediate trajectories and checking against the obstacles with point and polygon tests. And the algorithm is linear in the number of paths. With a distance, compared to a distance-based clustering with a manually tuned threshold, you can see that sometimes the distance between the paths is too low, and several classes are created, although all these belong to the same principal direction. And sometimes the distance is between the paths is too low for the threshold, and the paths are clustered together, although they correspond to different principal directions. And the proposed algorithm overcomes these problems. I'm looking forward to discuss the method further with you at the upcoming interactive session. Thank you very much.
Hi, good morning. My name is Yugu. I'm from West Virginia University, and the paper we have is a wide field optical flow aided inertial navigation for UAVs. Here's what we did. Our main objective is really to come up with a stable navigation solution. It doesn't have to be a complete solution for UAVs without GPS. And we know that insects don't have GPS. They can still fly well. And our solution is we have a sensor fusion algorithm that can integrate a wide field optical flow with initial measurements and laser range finder measure distance in navigation. So the result is that we're able to estimate the vehicle speed within about 1.4 meters per second. That's with respect to a fixed wing aircraft that has nominal speed about 32 meters per second, and altitude within about 1.5 degrees standard deviation error. And that's a non-drifting solution. And that's kind of in line with a typical loosely coupled GPS INS solution. And the benefit is, so what we're doing here is a very bottom layer of a navigation system that building on top of that, we can have collision avoidance and we can have visual landmark tracking and other things. But this, to keep the plane stable in the air is our primary objective here. So what we have instrumented on this research test that we have in the university, and we have multiple sensors for navigation. The sensors we use for this paper include a GoPro camera that used to generate the wide field optical flow, and industrial measurement units, and a laser rangefinder. We also have two additional sensors for choose. One is a mechanical vertical gyroscope that directly measures pitch and roll angles, and also a GPS. So the main idea here is that the wide field optical flow contains rich navigation information, especially pitch and roll angles that's not usually observable in the center of the field of view. So we're using an standard information filter to fuse those hundreds optical flow points across the frame with inertia sensors and laser range. And we also track the sensor bias in real time so we can calibrate them as we go. And so here are some results. And in addition to the numbers I mentioned earlier, the most important part is it's a non-diverging solution. So that if you see the figure on the right, and if you start with a very wrong initial estimation for your filter, and if you just do that reckoning, and it's going to be running at the wrong place. But once we turn on the correction from the wide field optical flow, and you can see it quickly converges to very low error. So that's our main result. I'll be happy to talk to you more in the interactive session. Thank you.
Hi. Hi, good morning, everyone. My name is Zheng Fang. Today I present the work that I did with Dr. Sebastian Strel. In recent years, several RGBD odometry methods have been proposed. However, they may fail in different kinds of environments. Understanding the accuracy change is important for us to choose the right odometry or to develop a more robust one. In this paper, 6 odometry methods were selected for comparison, namely LibreVision2, 4-ways, DVO, fast ICP, GICP, and the NDT method. We first compare the accuracy using the TUM datasets. We use the relative pose error metric to measure drift. Here we select 2 datasets for comparison. In our experiment, we found 4-ways got the best accuracy. To evaluate the robustness, we tested them in different kinds of environments and use the loop closing error to measure drift. The first experiment was in a long corridor environment. We found that DVO gave us the best result, while fast ICP and 4-ways failed due to the insufficient constraints and the repetitive features. The second experiment was in a more complex environment. We found that all methods succeeded in this environment. However, 4-ways gave us the best result. The third experiment was tried to compare the robustness against the illumination change. We found that depth-based methods were better, while sparse feature-based method totally failed. However, DVO can still survive from this experiment, except in some very dark areas. The fourth experiment was to compare the robustness against the fast motion. We found that depth-based methods were better. The reason may be that the motion blur and the large frame-to-frame motion degraded the performance of image-based method. The last comparison was the runtime performance. In our experiment, we found that 4 ways gave us the best speed and the lowest CPU usage, while GICP is much slower. From the experiment, we can conclude that the performance of each method depends on the quality of the RGB data and the environmental characteristics. If you want more details, I'd like to talk to you in the interactive session. Thank you very much.
Hi, good morning. We are from SRI. My name is Han Chu. So we propose a new vision-aided aerial navigation approach by integrating INU and the 2 kinds of visual measurements into a vector graph framework. So our approach can achieve very accurate navigation performance in GPS-denied environments using only INU and monocular cameras. The idea of our approach basically is that we generate a geo-reference database beforehand, and then during the online real-time navigation, based on the prediction pose, we generate the render image with a depth map. Then by matching the render reference image to the current video frame, we find the feature correspondence and get the 3D information through the features. And then we propagate the 3D information through feature tracks that can improve the performance. So here, that instead of talking about all the details, including how to convert the visual measurements into the vector graph, so we will just show a demo video, probably it's more interesting. So in the top left window is a render image based on the prediction pose and within a larger area. And the bottom left window shows the video frame that should correspond to the middle region of the render image. And the bottom right window shows a feature track, and the real-time navigation performance is showing in the top right window. So currently this can run around 1 to 2 hertz for the geo-registration. So here are some experimental results. So in these 2 large area GPS-denied scenarios, that without the geo-registration visual measurements, that the 3D RNS error can be bigger than 100 meters. But using our approach, that 3D RNS error is less than 10 meters. So you can see that compared to the ground truth, that using the differential GPS, that the yellow trajectory is more closer to the blue ground truth using our approach. And our framework actually covers the every frame SLAM formulation. So in addition to the geo-reference information, we can construct a dense 3D landmark point clouds in real time. So here shows the 3D point clouds. So if you are interested in the more details, I'm looking forward to meet you in the interactive session. Thank you.
Can you restart the call? I'm Mario Gianni, and I'm going to present our research work on real-time autonomous 3D navigation for tracked vehicles in rescue environments. Actively articulated tracked vehicles are currently used in search and rescue applications where terrain conditions are unpredictable and difficult. They are better suited for such tasks than wheeled vehicles due to the larger contact area of the tracks with the ground, which provides better traction on harsh terrains. However, remote control of all the mechanical components of such robots for either climbing stairs or traverse harsh terrain is very demanding for a human operator. Under this perspective, we designed a framework to allow tracked vehicles to autonomously follow 3D paths in cluttered environments. These frameworks comprise 3 main building blocks: segmentation and labeling of the point cloud acquired from the 3D laser scanner, building of the traversability graph of the environment according to the resulting segmented map, plan generation, and finally plan execution and adaptation of the active subtracks of the robot given both the path and the traversal terrain on which the path lies. Both normals and curvatures are estimated for segmenting, labeling, and estimating the inflated regions of the filtered point cloud. Here we can see an example of a segmentation implementation of point cloud of a rescue training area in Prato in Italy. Given the segmented map of the environment and the estimation of the inflated region, we first build a connectivity graph of the environment, and then we suitably weight the edge of the graph to obtain the traversability graph of the environment. This is an example of the traversability graph of the escape stairs in our courtyard of our department. During the path execution, slippage, shocks, and intermittent loss of track surface contact are commonly encountered during, for example, stair climbing, resulting in tip-over or rollover conditions. These phenomena are quite difficult to predict due to the lack of contact of proximity sensors. To maximize the track's contact surface with the ground and to improve stability on slopey surfaces, we extended the trajectory tracking controller on the robot with a statistical model assessing both the touch and the detach of the robot flippers with the traversed surface. This model is based on a support vector machine. During the control loop, the controller adjusts the flippers posture depending on the feedback provided by this contact sensor model. During the interaction section, you can play with our virtual reality environment in which you can see this framework, how it works. Thanks a lot.
Very much stop and go. The reason why they are more successful is that they have an interaction-aware navigation. So our motivation is to understand the human interaction-aware behavior during navigation in order to improve the navigation capabilities of robots. Our hypothesis is that interaction-aware navigation of humans can be modeled with the so-called non-cooperative game theory, and more precisely with the theory of Nash equilibria in games. So the goal of this specific work is to verify this hypothesis by analyzing motion data of interacting humans. So what did we do? In the first step, of course, we had to capture human motion data of interactive navigation scenes. And in the next step, we used this data to set up a game with all the players, costs, and cost functions, and to calculate the Nash equilibrium. Okay. Then we compared all the trajectories we have collected with reference trajectories, with the dynamic time warping analysis, time warping distance. And in the last step, we tried to test our hypothesis by looking if the Nash trajectories are more similar to the reference trajectories than all the other trajectories. So, and the nice thing, the results were very well. We tested it with confidence intervals and Fisher's combined probability tests, where the Nash trajectories are really more similar to the reference trajectories than the rest. So to conclude, we can say that we can model human interactive linear navigation with the theory of Nash equilibria in non-cooperative games. So this was just a teaser. I hope to see you in the interactive session. Thank you for your attention.
Good morning. My name is David Liu from Washington University in St. Louis, and I want to talk about layered cost maps for context-sensitive navigation. And so the context-sensitive navigation stems from a simple use case where we had a robot trying to drive from one side of a person to another. And this behavior is correct in that it finds the shortest path and does not collide with anything, but is problematic because it doesn't respect the person's personal space. And so we added a tried and true approach where we added a Gaussian around the person to the cost map so that the robot would prefer to drive slightly further away. And this approach has been tried many times before, and we were able to use it to run a number of experiments. However, it's very problematic when it comes time to actually update the cost map, and that is because all of the information is stored in a simple two-dimensional grid of values. And that's what we call a monolithic cost map. And as you can see here, the information from our proxemic adjustment to the cost map overlaps with the data from the other data sources, meaning that the update process becomes a lot more muddled and you have to recalculate the values frequently. Furthermore, there are semantic interpretations of the cost map that are not possible if you keep all of this information in the monolithic cost map. For example, if the previous values in your cost map tell you that there is a solid wall in front of you, but your current sensor data tells you that there's an open space, with the monolithic cost map, you are unable to determine whether it is, in fact, a door that has been opened or a glass wall which you should not drive through. So in addition to the fact that there is limited information in the update step, monolithic cost maps are also limited by the fact that they have a fixed update space, an ad hoc update process, and semantically fixed interpretations. And so our solution to this is what's known as layered cost maps, where we divide up each data source for the values that populate the cost map into its own layer, and then those values are combined into a master cost map where path planning is actually performed. And now the update process is a structured two-pass algorithm that goes through each of the layers, first to determine how much of the cost map should be updated, and then to actually populate the values in the master cost map. This not only alleviates the problems mentioned before, but also allows you to add numerous additional layers to make your robot navigation take additional contexts into its navigation planning. And also, since I'm a strong believer in open sourcing all of my code so that others may replicate the experiments, all of this code for the layered cost maps is available on GitHub and has been released into the latest releases of the ROS navigation stack. Thank you.
Welcome to my short presentation about omnidirectional 3D reconstruction in augmented Manhattan worlds. My name is Miriam Schwimbern from the Karlsruhe Institute of Technology, and this was a joint work with Andreas Geiger from the Max Planck Institute. As the title already says, we are interested in a dense 3D reconstruction of the complete environment around our sensor setup. Therefore, we use two omnidirectional cameras, in our case mounted on top of the vehicle on the left and the right side, and we use these set up at two consecutive frames. This means we get 4 image pairs, 2 spatial ones, and 2 temporal image pairs. Now we apply simple rectification methods and feature matching strategies to obtain 4 disparity images from the spatial and motion stereo pairs. And we combine these 4 image pairs to one resulting disparity image, shown here. This disparity image has its camera position parallel to the ground plane. And now we smooth the disparity image by assuming we have plane hypotheses for vertical and horizontal planes. And we assign each pixel to a plane hypothesis and select the best plane by an energy function model. We compare our results against ground truth from a Velodyne laser scanner, which also delivers a dense 360 disparity image, and obtain very good results. Here you see a 3D reconstructed scene from only 2 catadioptric cameras. So if you're interested to learn more how we reconstruct such scenes, let us discuss in the interactive session. Thank you.
Good morning. My name is Julio Godoy, and I'm presenting the work entitled Anytime Navigation with Progressive Hindsight Optimization. Our problem is multi-agent navigation in crowded spaces. Here, each agent has to move from a start to a goal position while avoiding collision with other agents and with static elements of the environment. And the objective is to reach the goal as soon as possible for each agent. For navigation, we use the ORCA framework because it provides collision-free motions for each agent. ORCA, in this sense, computes locally optimal motions for an agent. However, locally optimal motion is not always globally efficient for all the agents because of these myopic goal-oriented motions. With our approach, progressive hindsight optimization, each agent computes a set of velocities, but for a longer time horizon, updating at each time step its position and the position of its neighbors. So instead of following a goal-oriented motion like ORCA does, our approach simulates a set of velocities without committing to any of them. But it does not do this only for one time step, but for a longer time horizon. We start by generating simple trajectories of single actions, but if time allows, we generate more complex trajectories. Each trajectory is evaluated in terms of how much progress it takes for the agent towards its goal. And this reward is associated in hindsight with the initial action of the trajectory. So at the end, the final value of each one of the initial actions corresponds to the average of the reward value of all the trajectories that had this initial action. So when there are constraints in the environment, some of the trajectories will notice this, which will produce lower rewards for those trajectories, and this lower reward will get projected back to the initial actions. In this case, these two actions are going to have a lower reward, while this one is going to have a higher reward, so the agent finally is going to commit to this action. So it executes the actions, it updates its motions, and then it plans again. In this comparison, we can see how agents using our approach compared to ORCA, they have to reach the exit on the left side of the room. We see that agents using our approach can use the 3 exits of the room, while agents using ORCA are only trying to exit the room through this middle exit, which produces that they reach to the goal in lower time. If you want to see more videos, you can visit the website of the project, where also is the paper, and I'm looking forward to discuss with you our approach in the interactive section. Thank you.
Good morning. My paper is about 60 image-based visual solving for robot manipulated with and calibrated stereo cameras. Visual solving is a nonlinear closed-loop control process in which some visual alignment error is regulated to 0 in real time. This error may be expressed in the image space, which is commonly known as image-based visual solving. In classical IBVS, there are some common problems such as singularities and local minima. In this paper, we try to solve this problem by designing a new image Jacobian, using a combination of the real stereo camera with virtual octo cameras. A linear mapping between the poses in the Cartesian and the image spaces is calculated. In this figure, you see that there is a robot-based free object and a stereo camera system in an eye-to-hand configuration. To this system, we add 2 virtual octagonal cameras. We project this object onto these 2 virtual cameras, which give us 4 pixel positions. Since these 2 virtual cameras are octagonal, so these 4 positions can be used to calculate 3D object position in virtual 3D space, which is in pixels. For the orientation, we choose 4 points on the robot and vector and project them in this virtual 3D space. These 4 points are enough to calculate the rotation of the object. This gave us image Jacobian for the orientation. The position and image Jacobians are combined to give the final Jacobian, which is clearly square and 4 rank. This Jacobian is employed in a second-order slide model control. We integrate the virtual solving system in a HII scenario with a 6 degree of freedom industrial robot manipulate. We did 2 experiments for this system. In the first experiment, it shows 60 trajectory tracking. The left side is the teaching interface, the user teaching the desired position for the robot and vector, and then the robot and vector can automatically execute the same actions as the user. In the second experiment, we test some environment constraints such as singularity avoidance, the robot table avoidance, robot self-creation avoidance, and obstacle avoidance. If you want to know more detail and interested, please come to our interactive session. Thank you very much.
Good morning. My name is Nicolas Andreff. I'm from the Femto ST Institute in Besançon, France. I will present you a work which is dedicated to the steering of a surgical laser with the use of visual servoing. So this work is part of the MicroApp project, which involves the insertion of an endoscopic tool into the throat of a patient. At the tip of this endoscope, we have a micromanipulator that steers a laser, and we want the surgeon to design the path of the laser and the system to track the motion that is defined by the surgeon. So the problem statement is the following. We have to steer the laser with accuracy at a high frame rate on a trajectory which is defined by the surgeon directly in the image, and actually from a pair of images because the surgeon has a stereoscopic feedback. So in the image, we have the image of the laser. So if we look at the state of the art, there are some work where laser is used as an additional feature to visual servoing, but not used as it is. And also, visual servoing has made a lot of use of geometry as a key feature for efficiency. So the question we ask ourselves is, can we use geometry for efficient laser steering? So we went back to modeling, and we figured out that from physical stereoscopy that you see on the left-hand side, we can come up to a virtual trifocal geometry system by making an analogy between the laser steering system with a virtual image. And then using this trifocal geometry, we can bring up a controller in a few lines of code where we don't need to explicitly estimate the depth. It's implicitly taken into account by the controller. The nice thing in this controller is that we can prove the global asymptotical stability of the controller, which is very important in the surgical case because you don't want to have some failure at some time. And also, a key issue for surgery is that the system is very robust to bad calibration because you cannot expect the surgeon to recalibrate the system each time he's going to use it. So I'll show you the results if you come and see me at the interactive session. And the message I want to pass here is that you should always go for geometry. Thank you.
Good afternoon, everyone. Thank you for coming to my presentation. My name is Akbar. I'm a PhD candidate from RSJ University, the Department of Mechanical and Industrial Engineering. Today I'm going to discuss my research on a novel two-stage control scheme for robot and constrained visual servoing. So as many of you may know, visual servoing is actually a method to control the robot using the camera images. For this matter, we usually have the images coming from the camera, and it's compared to the desired image. And based on this comparison, actually, the robot is moved. So there are several limitations to this system. Some of are actually enforced by the system structure. So, for example, the camera has a limited field of view, and the objects might actually fall out of it. The other thing is the robot also have a limited reachability and motion. So some of the trajectories that actually we seek for the camera velocity might not be actually feasible to do. The other thing is the system might be prone to uncertainties in the system. So we have to take care of all these things for visual servoing systems to be practical. So here we see the two methods of position-based and image-based visual servoing. As you can see, one is actually good in the Cartesian space, but the trajectory for the image is not so good. The image might actually be lost after tracking of the features. In the other one, it's actually following the image very smoothly in the image space, but the trajectory that is created in the Cartesian space might not be feasible for the robot to do. So here we are proposing a two-stage controller. What we do in this two-stage controller is basically in the offline stage prior to the servoing. We assume an ideal system, no uncertainties, and we try to develop trajectories for the system's features, image features, and also the velocities of the camera. Next, when we are doing the servoing in the online stage, we try to minimize the difference between the current features with the trajectory that we form in the offline stage, and also the velocities of the camera. We try to minimize that using a model predictive controller. So here we try to actually address the constraints of the system in this minimization here. so that the system would be able to address the constraints of the system that I discussed before. So here are the results, some of the results that we have for this controller. As you can see, the controller is capable of handling the constraints in image space and both in Cartesian space. The velocities of the cameras are also showing that it's quite smooth, and you can see that the constraint that we have in the camera velocity here is also addressed. In another result we have here, we can see that the error of the image is much less than the previous IBVS system. That is going to be one significant impact of this controller. So I'd like to discuss this more with you in the interactive session. So if you will join me there, I'll be able to discuss it more with you. Thank you very much for listening to me. Thank you.
Hi, my name is David, and I'm with the Department of Mechanical and Automation Engineering of the Chinese University of Hong Kong. I'm going to present you some results that I obtained with my PhD supervisor, Professor Liu Yung Hui. In this paper, we addressed the eye-hand visual servoing problem. Most of us know that in order to implement this very well-known classical approach that I call, we need to know the position vector of the features that you're actually observing. If you don't exactly know where these features are located, you cannot directly implement this method. In a paper, we present two methods to cope with this problem. The first method that we present is just a state feedback controller. I can't give much details, but it has a very similar structure to the classical method. The difference is that we don't use the part of the Jacobian that depends on the depth of the feature point. We show that this method can enforce a stable servo loop, but when we try to extend it to several feature points, it's a little bit complicated. The second method that we propose, now we try to incorporate some numerical integrator. It's an adaptive controller. In order to use adaptive control techniques, we need to depart from the traditional depth scale kinematic plant. We add and multiply some terms in order to obtain this a more friendly mathematical representation, which we can linearly parameterize in terms of the unknown position. I'm going to show some simulation of how do we initialize our estimator, which is something like this. We need to get some offline data. Say you can do some trajectory and collect several image points and configurations of the robot. With these configurations, we compute what we call the projection estimator error. And with this error, we compute the adaptive parameters from our algorithm. Well, the scope of our paper is to show that the system is stable in the Lyapunov sense. And we show that once you compute these parameters, you can compute a very simple adaptive controller with an adaptive transposed Jacobian matrix. And as perhaps the major contribution is we show how can we stably couple these two different dynamical systems, the transform kinematic plant with the dynamics of the estimator that we have. If you want to know more details or to see our simulations and experiments, you can approach me during the interactive session. Thank you.
The next speaker hasn't shown up. Is the speaker after the next speaker here? Too late. And therefore, I suggest we ask questions to this speaker. What do you think?
Yeah, go ahead.
He's up for it. Let's have some questions for this speaker.
Yeah.
I have a question if it's needed.
Professor.
You said at the beginning that the depths were necessary.
I'm sorry.
You said at the beginning that the depth is always necessary, which is strange. So could you explain more in which case the depth is necessary?
How do we get rid of the depth? No, we don't. Actually, this paper, it was my supervisor, he has some issue with the depth. He always tries to use controllers which do not depend on obtaining or structuring the points. So what he wanted me to do in this particular paper is to show what conditions are needed in order to enforce a stable, the Lyapunov stable servo loop with both just static state feedback controllers and also if you include adaptive controllers as well. So that's more or less the the reason why we did this study. I don't know if that's what you were actually asking. Okay. Well, I'm not an author of this paper, but the author of this paper could not come. He had some visa issues. So I'm going to very roughly present what he did on this paper. The title of this paper is Visual Servoing-Based Trajectory Tracking of Underactuated Water Surface Robots Without Direct Position Measurements. The authors are Wang Kai, Liu Yonghui, and Li Lu Yang. They're all from the Chinese University of Hong Kong. Well, the authors, they use, in their paper, they developed the dynamics and the kinematics for an underactuated system. They use 3 different reference frames. One is the inertial frame, and they fix another reference frame on the mobile robot, and they use another reference frame to characterize the measurements of a camera. The problem that they are addressing here is a trajectory tracking problem formulated from a control theory perspective. What they're trying to do is they want to track the start trajectory without using any global positioning measurement sensors. So they only using cameras and IMUs. In order to generate this start trajectory, in their paper, they need to solve some equations. Since it is an underactuated system, you cannot just give any trajectory because some of those cannot be followed by this system. Well, the authors in their paper, they present their controller, and since they don't use a global positioning system, they propose some estimator to estimate where the position is. They fuse the measurements from monocular vision and also some measurements from IMU. Just some experiment, I guess they're just trying to follow this trajectory. And there won't be any interactive session for this one since he didn't come, so I guess the best I can do is just to show his video. So this is the prototype that this student developed, and so it's just following some trajectory along some lake on campus. This image over here shows the tracking of several features that he's just tracking along the lake. So, yeah. So the robot follows what he's supposed to follow. Just some results from what this student did. So tracking results and velocity tracking results. So if you want to know more details of this, there won't be any interactive section, so you need to go to the paper itself. Thank you.
Good afternoon. My name is Victor Navarez. I'm a master's student at the University of New Mexico. This is work I did with my advisor, Professor Ron Lumia. A centralized motion algorithm is an algorithm to calculate of the image Jacobian of an unknown system. This means that the intrinsic and extrinsic parameters of the system are not known. Calculation of the extrinsic parameters online is a difficult problem which usually requires calibration targets. The CMA is capable of accurately calculating these parameters online in a short number of iterations without any knowledge of the system. The CMA depends on a motion coined centralized motion. A centralized motion is where a single feature point, which we labeled as a centralized point, retains the same pixel value throughout the motion. For example, if a motion was made about the camera's x-axis, then the centralized point would retain the same pixel value throughout that motion. In order to achieve this type of motion, the trajectory needs to be circular. From this, we know that the centralized point's depth is the radius of the circle. If the estimated radius is smaller or larger than the actual depth, then the error from the pixel is directly associated to the depth error. This means that if a centralized motion is made and the centralized point's pixel value changes, then that change in pixel value is proportional to the depth error. From this, we made an error model that is capable of calculating the image Jacobian. we've found that our error model is very stable and converges very quickly. In our experiments, we found that the CMA is capable of converging in an average of 4 iterations. Even with noise introduced into the system, the CMA converges, but with an error related to the noise introduced. From these fast convergence and these robust results, the CMA proves that it can calculate an image Jacobian of an unknown system. I look forward to discussing this paper in detail at the upcoming interactive session. Thank you very much for your time.
Hello, my name is Nate Macias, and today I'm here to present to you visual guided robotic block stacking, research conducted at the Center for Automation Technology and Systems at the Rensselaer Polytechnic Institute under the guidance of Dr. John Wen. So robots are precise and efficient at performing repetitive tasks, but they lack the innate ability to manipulate objects. Bin picking has long been a research area in the field of robotics that aims to provide robots with the ability to manipulate randomly ordered objects within their workspace. The 3 main challenges that a bin picking system must address are scene interpretation, object recognition, and pose estimation. These challenges are difficult due to objects in the scene may be clustered together, creating a cluttered image. Objects may be piled on top of each other, creating occlusions, and environmental conditions may be poor, such as bad lighting. So the goal of this research was to develop an integrated system for the complex manipulation of Jenga blocks. LVAR binary markers provide the basis for determining the block's pose within the robot's workspace. The use of markers simplified object recognition. Each block has a set of unique tags used to assign an ID, estimate the block's pose, and determine the necessary graphs to remove it from the field. The system consists of a webcam, computer, and a Staubli TX40 6-degree of freedom robot arm. All system components are integrated through Robot Rack and Tour, and the data is processed in MATLAB. To locate the blocks, the robot performs a zigzag pattern, shown above. Cost is a measure of how difficult it is to remove a block from the field, and is used to determine the queue order. If all blocks are on the same plane, the outlier is removed first. If the blocks are piled on top of each other, the highest block is removed first. Using a Gaussian discriminant function and training data, the system is able to determine when it has successfully grasped a block. So all these components provide the tools necessary for the system to determine when a set of blocks are ungraspable and perform an appropriate action. So it broke up a set of blocks. Disassemble a complex pile of Jenga blocks. Assemble Jenga tower layers, and eventually stack those layers. Thank you. I look forward to discussing my research further with you at my booth later today.
Good afternoon. My name is John Zulick. I'm from the University of Waterloo. I'm presenting the work of my former master's student, Abdullah Hojoy, and the work is visual servoing with an RGBD or a Kinect sensor, and he developed a 2-phase controller. Let me provide some context first for the work that he was doing. Originally, the project I wanted him to work on was kind of selfishly motivated. I actually wanted him to develop a system that was a fetch system. The robot hand would throw an object to a dog. The dog would come and deliver it to the robot. The robot would pick up the object and throw it back. So selfishly, I wanted to bring my dog to school and give him something to play with. So in essence, the 2-stage algorithm that Abdullah developed, The first phase is solely driven on the image data. The representation of where to drive the controller is based on SIFT features and a collection of them represented as a bag of words. So using a standard trajectory algorithm, the camera in hand is driven to a location where in the second stage, which is driven just by the depth data, the robot would move in a straight trajectory and grasp the object. So this shows the setup that we had with the camera in hand. The next slide shows what the camera is seeing. In this case, it's obviously not a dog toy, but driven to the parakeet. The depth map that is being seen in the first stage, driven to the parakeet. Another representation of that. This was the last one. And this is looking from the parakeet's point of view, the Connect sensor aligning itself up. So there's a couple of stages missing from the overall project that I had originally suggested. So where do we stand right now? So my dog's still left in the cold. I'm not allowed to bring the dog to the school, and he has nothing to play with. But the work that Abdullah did set up is a first step to achieving this end objective. Thank you very much.
Good morning, my name is Nicolas Kazi. I'm a PhD student at INRIA Rennes in France. I'm gonna talk to you today about the work that I've done consisted to define a new method of pose error correction for visual features prediction. Let's consider a system composed by a moving camera and a target with visual features tracked on the camera image plane. Visual features measurements are available until arriving an event at T0 which impede more measurements. This event can be an occlusion or features leaving the camera field of view or error of image processing. The problem is that by the time this event disturbs measurements, visual features locations change on the camera image plane during the camera motion. So the solution consists to predict locations of visual features exploiting the camera motion in order to recover visual features after the event or to build a model predictive control. In our system, we set X as the pose of the target in the camera frame, which gives us a location of visual features on the camera image plane that you can see in red on the graph, that we can compare to the model of visual features on the camera image plane in blue, coming from a wrong estimated model of the target pose in the camera frame. And we can see that they don't match during the prediction because of the difference between real and estimated model visual features at T0. But we can use this difference to build three different corrections. The first one, which is usually used, consists to correct only visual features, but does not correct the pose, which will affect the prediction. That's why we propose to correct the pose, the model pose, but which does not guarantee to correct model visual features at T0. That's why we proposed a last correction, which guarantees to correct the model pose and the model of visual features. Of course, if you are interested for more explanation about those three corrections, I invite you to join me into the interactive session. Thank you very much.